Good morning, good afternoon, good evening, good night, wherever you are. And thank you for joining this presentation remotely. I'm glad to be able to present to you live this presentation on the flexible future of RF. In fact, when I was contacted by the organizers several months ago about to deliver the keynote speech for RFIC, I just said, wait a second. Have I done this before? And I realized actually I have. So I went back and looked at my presentation and slides and said, okay, what happened? And it was back in almost 20 years ago. It was May of 2001. And I found actually my slides. And so I started looking at them and said, okay, wait a second. So these are some examples of some of the slides. And it actually made me think about how RFIC has changed and using that as a template for how its future going to be. So here are a few examples that I took six slides out of the deck that was presented in May of 2001 as the keynote speech to RFIC. And one of the interesting things that caught my attention is that some of the key concepts that still is applicable were there. The fact that silicon allows us to turn sand into money, and then also the fact that, there are all these interesting things that we can do with it from, the component levels. For example, this is what they later on became known as a DAT, distributed active transformer. At the time, we still called it circular geometry active transformer, or a certain kind of like dual band concurrent LNAs, or the concepts of phased array at 24 gigahertz using silicon, things of that sort. So interestingly, so that made me think, okay, what happened to some of these phases that the RFIC has gone through? And so here, like next few slides, I'm going to kind of go through that thought process and what, at least from my view, what has happened. So there was basically this era of what we call the pre-RFIC dominance, which basically where this is the traditional era of microwave design, RF design and microwave. Things are made out of discrete components. You basically put them together. A lot of this stuff, especially the higher frequency stuff, started in from the waveguides, and there was a lot of microstrip design. There were few components, and these components had essentially more they were expensive, they were kind of like bulky generally, and they were kind of like attached, as you can see that from some of the examples on the right hand side. And the other interesting thing is that the system specification was kind of like flowing down to RF design, and the RF designers were just implementing that in that time period. Now, so the other interesting, what happened is that in the late 90s and early 2000, RFIC, especially in the silicon incarnation, and especially CMOS RF, was still considered a kind of like an academic exercise. And that was not considered a good thing, by the way, being an academic exercise. Now, there were multiple years at ISSCC and other conferences. There were panels literally called, does CMOS make sense for RF? And actually, a good number of people were saying no. And so it was interesting. And so this started kind of like these block level components, like the ones that I showed in the previous slides from the RFIC 2001 talk, started emerging. So there were some examples of like the early works are shown on the right hand side, where people started making blocks and smaller units of system and demonstrating that it can be done. Now, and then everything had to be proven, kind of in the sense that, a lot of the conversation was about the performance numbers. Yeah, yes, you may be making an amplifier, but it's not really an LNA because the noise figure is so high, or the power output of the power amplifier, if you make it in CMOS, or efficiency, the phase noise, etc., etc. And this was basically for two reasons. One is that many of the architectures people were thinking about at the time to use these components were essentially directly borrowed and copied from the RF and microwave design, the classic RF microwave design. Now, those architectures were built the way they were because the trade-offs are different in those cases. The classical discrete design has expensive transistors. Passives are cheap, but transistors are expensive. And then you have, in essence, large mismatches, so you can't really count on device matching and things of that sort. And then the other part of this is that the thinking was that okay, we have a certain system, and if you can make an RFIC for it that matches 1-to-1 with the, kind of like the gas or 3-5 or compound semiconductor component that we have, if there's a 1-to-1 match with that, great, maybe we can use it because it may be like so many cents cheaper, but otherwise, don't even talk to me. As a system designer, I don't care. And when you started talking about things like, for example, the couple of slides that I showed earlier from the 2001, where you talk about new architectures for example, doing phased arrays or things of that sort of time, and it was really dismissed as academic wishful thinking that the architectures would be changed because of the fact that you're doing RFIC design. But RFICs were different, and they were a force of nature, and they had good things and bad things about them. So one of the interesting things about them was that the breakdown voltages kept going down, and they were kind of like becoming punier and punier as the transistors were. The other thing is that there were a lot of crosstalk issues, but there were several interesting things from an RF perspective, is that because the whole thing was much smaller, things stayed lumped to much higher frequencies. You could treat them like lumped circuit, and the components could be matched nicely. So you could have reasonable, much better matching than you could have off-chip components. And the problem was going off and on-chip and off-chip. In these cases, the interface was where most of your challenges arise. So this led to a transition that in several different fronts. One is that you want to stay on chip as much as you can. And the other thing is that you wanted to really change the topologies and architectures and see what are the new things you can do that you couldn't do before without like RFICs. Now, this led to some of the developments that kind of like I've shown some of the pictures from our work in the past. On the right-hand side is 24 gigahertz transceivers and 77 gigahertz transceivers, and like later on 300 gigahertz phased arrays and things of that sort, all done in silicon and CMOS. And one of the things that became clear is that when you went to higher frequency, you could integrate more and more, even the antennas and radiators. And when you did that, eventually you got around a lot of these interface problems. And then you really came up with architectures that were unique and particularly tailored and advantageous for RFICs, as opposed to things that would be very, very different in the case of the discrete design. And this really relies on the fact that, first of all, transistors are free. You have reasonably good matching. And the fact that once you integrate everything on chips, you can create very interesting electromagnetic structures that can do things that you can't really do that easily in discrete. And this really came from a trend that was kind of like, I've articulated it many, many times in different ways, and other people have too, which is basically a transition from I call it sometimes the big elephant to the army of ants, or you could say in this case, to use the Wizard of Oz analogy, the transition from a big lion to the army of mice. And this is a paradigm shift that basically is really generated by the unmatched complexity to mass and cost ratio of integrated circuits and the ICs and RFICs. And this is kind of like changing things around. So instead of saying that I'm starting with a known existing architecture and I want to design the components and block levels for this architecture at higher level, you could say, look, I am going to change my architecture and even system design and application even, and look at the very broad range of applications that allow me to take full advantage of RFICs and what they have to offer. And so in this talk, I'm going to give you a few examples, and there are a lot more examples from our work, but kind of like I would just like try to focus on some of them. Now, one of them is basically this concept of flexible phased arrays. So scalable and flexible phased arrays. So something that you can make essentially as a fabric, something that you can roll open, something that can change shape. It's very lightweight, and it allows you to make a very modular and scalable system that can be deployed and collapsed. It's self-contained and reconfigurable, and it's fully integrated and robust. Now, it does everything locally. It generates power synthesis and frequency synthesis locally, and it will be very efficient for power distribution. Now, what applications you can think about for this? A broad range. Anything from active fabric that you can use for a variety of applications, to terrestrial communication systems, to space deployable structures, and so on and so forth. So, for example, you are all familiar with wearables, but if you have these flexible RF systems, you can think about them, making them part of your, apparel, and you can use it for sensing and actuation and control and all sorts of interesting things. The other thing is that, of course, if you can make such lightweight structures, and it's particularly useful for space, because space, in things that go into space, mass is one of the very major parameters, and it really determines the cost to a good degree, because you really pay in dollars per gram. And so the idea here is that a lot of this, like space-based internet systems and low Earth orbit internet systems, you can make them very, very lightweight, and they can be powered by solar energy and form an array, and they can actually communicate and send information, all those things. And these kind of structures can be very useful because, as I'll show you later, they can be compactly packed and then deployed in space. Another application, which is kind of like a little bit more ambitious and longer term, and people have talked about it a long time, and it actually started in science fiction, is the idea of space-based solar power. So this concept of wireless power transmission is a very interesting concept, and I will talk about the terrestrial applications of that later in this presentation. But so one of the interesting things about it is that the space-based solar power concept is that you basically, if you deploy arrays in space, you can collect the power and transmit it. And the advantage here is that really you get about 8 to 9 times more power in space, because you don't have the cycles of the day and night and the seasons and the clouds and things of that sort. And then you can transmit it wirelessly to ground. So this concept has been around for a long time. A lot of people have played with it. And at Caltech, we have also kind of a system which is made of modules that are operating independently, or they're generated, and they're doing formation flying, and each one of them consists of forms a very large array, but collaboratively and in concert, all of them form a very large array for power transmission. So these things, the idea here is that they are all operating in synchronization. They're extremely lightweight, sail-like structures that you deploy in space, and that's what makes it cost effective. And you can use them for, if it's used for wireless power transfer, you want to probably use a dense array or sparse arrays for other applications such as communication and remote sensing. Now, the hierarchy of our design, if you look at it, it starts with the tile. So it's basically, the tile is a unit building block, which basically will contain, and we'll talk more about it in RFIC, and it basically is the unit that you use, and you can scale it. It doesn't necessarily mean that it's mechanically separate. They can be all aggregated, but it's the unit building block that's repeated. And what you see here is that on the one side, you have this solar concentrators, which was kind of one of the designs that we implemented. And on the back side, we have the photovoltaic array, and on the next one, you basically say that you can make these larger strips of that, and these form modules that can be up to 60 meters by 60 meters when deployed fully, and then in aggregate, they can actually form things that can be quite large and fly in formation. Now, these things are, as they are very flexible, you basically fold them and package them and then wrap them into that, like a small cylinder that's like it's shown on the lower right, and then you can use them to unwrap it. And this is an example of how this wrapping and unwrapping looks like, and then eventually they would get stretched, and as a result, they will get deployed in a way that would allow you to create a structure that can be self-sustaining. It's still flexible, and we'll talk about the issues associated with that and how to deal with that. And the interesting thing is that now these structures will have local power generation through photovoltaic, and the power is locally generated and locally used, so there's no need for the potentially high mass distribution of the power, especially DC power, because of the I²R losses. And instead, you're looking at a situation where you can have local power generation and usage, and all you distribute is control and timing information across each one of the modules. Now, each one of these tiles, if you look at it, so this one shows the top view and the bottom view of that. On the top, on one side, you have the photovoltaics, where you have, in this case, you have a concentrator, and if it focuses on a narrow strip to minimize the mass. And on the other side, and there's an RFIC, which is at the heart of the system. And then this RFIC generates power that feeds these different antennas and radiators, and do a microwave wireless transmission that can be used for a variety of applications. Now, the RFIC that's used in this system, in this example that I'm going to show, is basically operating at around 10 gigahertz. and it basically it consists of 16 different independently controlled channels that generate power. So the DC to RF conversion is done through an amplifier. It has frequency synthesizer. There's a low frequency reference that's distributed to them, and there's a frequency synthesizer that takes this like 50 megahertz reference and up converts it in 2 stages to RF of 10 gigahertz, and you can do a lot of things. Obviously, it's extremely lightweight, which is conducive to this operation. You can see it's like 8.5 milligram. When you look at that chip, and it's not even thin. And now, so the next couple of slides show a hierarchy of this RFIC, and we'll go through that quickly to give you a sense. So there's this like RF reference coming in, and it's just, there are 17 PLLs on this chip actually. So there's a low frequency PLL operating at 2.5 gigahertz, and then there's a high frequency one that operates at it takes a 2.5 gigahertz signal and translates it to a 10 gigahertz signal. So now what happens here is that as you go through this process, you will see that and basically what you have here again, and each one of these, and the chip is really broken down into 4 quadrants. So you can see that on each side there are 4 outputs that we call them a power quadrant, and they're fed through these signals. And each one of the power quadrants, this architecture is shown here. So this 2.5 gigahertz signal comes in, it's distributed. There are these clock multiplier units that generate a 10 gigahertz and also can produce a phase shifting. And then there's a rapid phase control in case you wanted to do modulation and things of that sort. And then there's power cores. There are 4 power cores that are actually in this case are stacked in a group of 4 in this chip, and they are basically sharing. So DC wise they are in series, but in they generate 4 different RF signals, and each one of these power cores has a fair amount of sophistication. And again, I'm not even going to go into the deeper levels of transistor level in this presentation, but there's a fair amount of signal control and power, PVT, independent biasing and monitoring of what's going on, and a fair amount of stuff goes into it to make sure that there's an efficient up conversion of power as well as a well-controlled one going forward. So now this is the RFIC part of it, but there's also an associated part, which is the part associated with the radiation. So this is an example of one of the radiators. This is a collapsible structure. This is the second sheet of material that contains the antennas, these particular antennas that sits on it, and when it's actually rolled and compressed and collapsed, it collapses down, but it kind of like pops open, and when it does, it provides the antenna. So this is a picture of it, like in 4x4 small array of those, and you can see how thin this layer is. Actually, it's almost translucent to the light, and you can see what happens. So now with this, you can actually create an RF layer. So this is a 2-layer structure that contains everything. So here's the chip, and then you have the RF, the antenna. So all of these are driven by this chip, and all of the RF signals generated there. And the active part of this is essentially this middle part. And there are variations of that we've made. And this is the one that basically the RF part is combined with the photovoltaic and system that collects the power. And you can see in aggregate, this has a mass of 16 grams, and it's like the RF part of it is about 7 grams. And these structures are quite flexible, as you can see. So this is the RF segment of that, and these connections are conducive to making a connection, making the connection from the base RF port to the antenna layer, and you can bend them and roll them and do all sorts of interesting things with them. And but as a demonstration, these things actually are capable of creating different kinds of focal points, and do all sorts of what we call the RF lensing and focusing functions. Essentially, they are operational both in the Fresnel, which is a radiated near field, and Fraunhofer, which is a radiated far field at the same time. So on the lower right, you can see an example of a focal point formed here, and you can see that by doing, you can control it and form a focal point similar way to a lens, and this subsumes the far field beamforming stuff that's normally done. So, and here's an example of this basically operation where basically you can see that we have a solar simulator on the top, illuminating the light, and then you can see now the RF power is generated and transmitted and recovered by the second board, where basically it's powering an LED. And to demonstrate that this is actually power coming from that, I'm putting my hand in there to make sure that it actually demonstrates it is real power. And this is the bottom view of this, which again, the same thing, shows the array. It's transmitting the power, and you can see it's quite insensitive to the rotational angle and the polarization in this case. And you can see that it's operating exactly as designed. So this is a tile, and then you can take this tile and take it to the next level, which is basically make a larger unit off of that, which is now, here's an example where you're using 16 of these chips to power and generate a 256 element array made of the same material. And what you can see here is that now this is a larger array, but again, very conducive, very scalable. And what happens here is that you can make it very flexible. Now, the interesting thing is that once you have something like this, there are some very interesting algorithmic variations on this thing that you can do. And there's some interesting math involved here using some pseudo orthogonal bases. That's quite interesting. And again, I'm not going to go into the details of, but there's a fair number of interesting aspects to it. And then there's another part, which is basically, can you actually create and focus beam? And do focusing in different directions. So the plots on the right-hand side show that you can actually be centered, up, down, right, and left. And there's actually a talk at IMS this year that goes into more details of this. And I encourage you to go and take a look at it to understand what's going on with more details. And the most interesting thing about this is that now the systems, because of the way the algorithms work, are actually now quite insensitive to deformation. So we actually had a situation where we had formed a spot here, a focal point, and then we deformed the array, as you can see, mechanically deformed. And of course, everything is messed up. And then once it refocuses, again, it allows it to be able to kind of get this going. Now, the interesting thing about the system is that if you look at the areal mass density of this thing, this is the world record at this point. This is about like 670 grams per meter squared for the system. And that includes everything, the RF array and the electronics and the photovoltaics and the structure that supports and all that necessary. And we expect this to easily go down by another 30% or so, like 450 grams in 1 year. And long-term designs are expected to reduce it by an order of magnitude to an asymptotic, what we call an asymptotic limit of a 30 to 50 grams per meter squared. And just to give you a sense of reference, the typical office paper grammage is about 80 grams per meter squared. So this would be kind of like, in terms of the mass density, would be comparable to some of the thinnest sheets of paper that you can achieve them. Now, interestingly, if you have something that flexes and bends, you have to be ready to deal with that. Now, there are different ways to deal with it. And one of the interesting things is that you can actually have developed these systems and architectures that allow us to do a local shape determination from the measurements. So we actually have local measurements where there are transmitters and receivers on each IC. And using the local measurements, they can actually determine the shape of the array. And to do that, one of the interesting things is that this is an example of that. Basically, what you see is that we just made the structure. This is a 1D example of that, where the array is being deformed dynamically in real time. And as it's happening in real time, we are getting distance estimates of different parts of the array and measure of the array. And you're using this information to do a dynamic shape measurement and self-correction. And what this is that in this plot, this is an actual measurement plot where you can see that without doing this, of course, as the array is deformed, the power that's received at the location away from the array is fluctuating quite a bit, like the red plot. But then as the correction is happening, a lot less fluctuation is observed at that distance, which basically shows that the system can self-correct to a good degree. Now, another kind of systems that would be very interesting and take great benefit from the RFIC are these so-called origami inspired structures. So these are structures that allow you to mechanically change intentionally shape of the array. So this is like an example of these things that we developed, and we developed our own RFIC for this, and we created these origami structures that can take the array and make it flat. You can make it cylindrical or spherical. And then you can see that by doing this, you can actually create an enhanced aperture that looks bigger at different angles, different from the the normal angles. So depending on which direction you're looking at, you can actually the system can deform itself and change its orientation to create the best aperture over a broad range of angles dynamically. Now, so we talked about the wireless power transfer, and one of the interesting things that happens with the wireless power transfer is that over the years, we actually developed several generations of these things and experimented quite a bit with these. So these actually are four examples of the things that we developed from 2.4 gigahertz to 5 gigahertz to 10 gigahertz to 24 gigahertz. And now it's being commercialized by Guru Wireless for wireless power transfer. So you can see that the equivalent of a 2x4 elements, these are actual physical sizes in comparison, how it scales. So when you go to higher frequencies, you are able to get more precise focusing. You can get higher power and longer range and a smaller size for your system. And so, these were kind of like as a commercial implementation, so that you can make scalable arrays that scale up very large to large scale. So you can see that using this unit building block that has the RFIC at its core, you can make very large arrays, and you can make mobile chargers that basically go around and find the devices to charge, or you can have stationary one, and you can have all sorts of different kind of and different aspect ratio, different size systems on the what we call the recovery units, the ones that receive the power. And in the next, and here's a video of some of these applications in real life. So one of the things that so you can see is that, so this is, for example, a generation unit, a GU, that's transmitting a power at a large distance. I believe it's more than 30 feet here. And then you can see that it's driving this propeller at a distance, which is basically running real life. Or this is another example where a unit on the ceiling is dynamically sending power, and very quickly and rapidly can track the devices and find the new locations and send it to the desired location and nowhere else. So it's very selective, very well controlled, and very rapid, that basically it can allow you to send the system, the power to different locations. And not only in one location, as you can see in this example, it can actually send it to multiple locations. So first it's being sent to 1, and then now to 3, and then eventually to 4 different light bulbs simultaneously are being powered by that unit. Now, this is another one where the focal point is dynamically moving with this car, with this little car that doesn't have any batteries in it, and it's entirely powered by wirelessly at 24 gigahertz. And this is another example of the mobile charger, if you will, that basically has some energy, and it basically walks around in the office or in your home and finds devices that need power and delivers power to them in real life and in real time. So these are some of the examples of some of the things that can be done with these systems. So now let me just try to wrap up quickly here. And so I believe that actually there's a very interesting flexible future for RFIC, where there's a lot of new applications that can be enabled, and I've listed some examples of those. And it's really up to us to take this amazing opportunity of being able to integrate so many things, and not only address the existing applications, but also come up with new ones that are very, very interesting and can open up huge new markets going on. And I think there's a lot of opportunities for new architectures, new designs, and new ideas to be implemented. And I want to kind of give you a little bit of a cautionary tale from the past. So these are some of the quotes that I could verify that have been said about how, essentially there's no real kind of like invention beyond what has been already invented, and things along the lines of everything that could be invented has already been invented. And this is a really, really dangerous way of thinking, and it has been proven wrong in the history multiple times, and it will continue to be proven wrong. And my message to you is that, especially to the young and the young at heart of you that's listening to this thing, is that you really need to be inventing the future, and you are the future that you're going to invent. And it's very important for you to not listen to the naysayers and actually go ahead and do it and prove them wrong. And I think it's incredibly important for every one of you to invent this flexible future in the best way you can. And remember that future never loses to the past. And with that, I'd like to thank you for your attention.